All good? All right. During the break, one gentleman asked a very good question. And I must admit that I probably was a little bit confusing. And I would like to come back to this point and make it clear. So when we are talking about continuity equation, so the best way of not getting confused is to refer to continuity equation as written in this form. This is the continuity equation. Then there are sort of modifications to this equation that might be also called in literature as continuity equations, but they are not. This is the continuity equation. If the density is constant, then we derive this condition. That's what we've done. It comes from continuity equation formally, but this, even if it's sometimes also referred as continuity equation, this is actually incompressibility condition. Continuity equation, incompressibility condition. Fluid is incompressible, so volume of the fluid cannot be changed. That's what that is. But because it can be derived as a particular case of the continuity equation, frequently it is referred in literature as continuity equation as well. And this is a little bit confusing. So that's something to keep in mind. Okay? All right. Now we're back to our semi-lecture, semi-tutorial exercise. So we were able to write down system of equations, linear equations with the constant coefficients, for the powers of dimensions as we followed the so-called pi procedure. So let's just look at this system of equations once again. So, and you can see that there are 6 unknowns, but only 3 equations. So the matrix has dimensions 3 by 6, which means that the rank of this system is at most 3. So those of you who are not familiar with that, it's not really consequential if you don't know the terms, but in the language of linear algebra, this is rank deficient matrix, and the matrix of this type cannot have rank larger than the smallest dimension of the matrix, 3 in this case. And by rank we mean the number of linearly independent rows or columns. And again, I don't want to go too far on a tangent, so to explaining what linear independence and dependence is, so hopefully you will know that. Well, our goal, practical goal, is to solve this system of equations. The question is how. So I will just take a very simplistic approach without fancy terminology, and I will tell you that in order for us to have a hope to solve a system of equations, it must have the same number of equations as the number of unknowns. Simple as that. So we have only 3 equations, so therefore we can solve for only 3 unknown variables. Therefore, we need to choose what we will solve for. And this choice is completely arbitrary, up to you. And in that case, I suggest just something which is more or less obvious. So what we can try to do is to find the first 3 unknowns in terms of the rest. First 3, by that I mean in the order of appearance. So, namely, I would like to find coefficients A, B, and C, 3 of them, assuming that D, E, and F are just known parameters. So that's what we will try to do. So how is it done formally? Formally, it can be done in a rather just, I think, easy to remember way. So what we need to do is to cut out a matrix, a larger square matrix out of this full matrix. So what do you think is the largest square matrix that we can inscribe into this big matrix? 3 by 3, right? How you choose this matrix, 3 by 3 matrix, does not really matter. But obviously the easiest way is just to take the first half of it, right? So therefore, if we just separate this, cut this matrix into two parts, one is square and the second one happens to be square as well, but that's just coincidence. So the first one must be square, the rest doesn't matter. Whatever is there, we will deal with that, okay? Then, what we have is essentially a system of equations which can be written like that. So 1 minus 3, 1, 0, 1, 0, 0, 0, 1. And this system, or these rows, multiply, or these three columns, first three columns, they multiply the first three coefficients. Remember, just the standard matrix vector multiplication. So this is multiplied by that, this is multiplied by that, this is multiplied by that. So that's exactly what we want. We want to have three first variables cut out. So therefore it will be A, B, and C. So whatever is left is to be considered as a right-hand side. We just push it into the right-hand side. And in that case, of course, if we push it into the right-hand side, we will get all these with negative sign, right? So we will get 1 minus 1, 0, 0, 1, 0, and I don't believe this is supposed to be there, right? So it's just me touching it. And the last one is 2, 2 minus 1. And of course, this is multiplied by D, E, and F. So, okay. Now our goal just to solve this system of equations, and this is three equations with three unknowns system with the right-hand side, which is written like that. Okay. So, before I go any further, a couple more observations. So just by luck, we can see that the left part, left-hand side part, contains a matrix which has two diagonal elements. Right? This one is full row, but these ones are two rows with just elements. So therefore, that means that coefficient C and coefficient B can be essentially read out of this equation straight away. No solution is required. So it's just a matter of luck in this case. So generally you would need to invert this matrix somehow, but in this case inversion is not really required. You just say that, let's say, I start from the back. C is equal to, so, and you just multiply by, and you will see that it will be multiplied by 2D plus 2 multiplied by E, right? So this times that, minus F, and there is a minus in front of it. Okay? All right, tell me what B is. It's very simple, right? In this case, it's extremely simple. It's just minus E. And I will ask you to compute what A is. So in that case, of course, you need to, by now you know what C is, you know what B is. So tell me what A is. So A is equal to whatever we have on the right-hand side, plus 3A plus B, plus 3B plus C. So tell me what the final answer is. Yep.
In the case that's a penny, or the matrix form like 6 or 6 and 6 plus in a matrix. Now you're writing C the version.
So if I understand your question correctly, so that was my original matrix. I cut it in halves, right? So, well, in this guy, well, my goal is to cut the largest square matrix out of it. square matrix in this case is 3 by 3, and I chose to cut the first part. So essentially what I want is to create matrix 3 by 3 and move the rest to the right hand side, so that on the left hand side I have a square matrix. Square matrix can be inverted, or system can be solved. Does that answer your question? Okay. All right, so what's the answer for A? What is it?
Anyway,
So A is
nothing. The D minus F.
T minus A,
Minus E minus S.
right? So am I correct?
D minus F.
D minus A. So I have C, which is given by this expression, B, which is given by this expression, and A is equal to this expression. Okay? All right, so good. Really, how you solve this system of equations, it's up to you. Whatever works, I do not insist on anything. So the conceptual thing here is that you, out of the big matrix, you need to cut 3 by 3 matrix and push everything else, a larger square matrix, and push everything to the right-hand side. Okay, so now what I will do, I will simply rewrite this answer in a vector form. So I will glue all the coefficients back together. Namely, I will write A, B, C, D, E, and F as a large vector. Okay? Then, and unfortunately I moved from the previous screen, then what I will need to do is to write the expressions for these coefficients, all 6 of them, using the previous result. Okay, so refer to your own notes and see what happens. So first of all, I will have I used since I use square brackets, I will continue doing that. So remember, I had to introduce 3 parameters. So I will draw 3 placeholders here for vectors. And in front of these vectors, I will put coefficients D, E, and F, plus, plus. Now, what I would like to do is to make sure that my coefficients are factored out and the numerical coefficients fit in these columns. Namely, for example, F, of course, is equal to F. So in order to create F on the left-hand side, I don't have D, so I'll put 0 here. I don't need E, and I will put 1 here. Is that clear? So to create E on the left-hand side, I don't need D, I need E, and I don't need F. So to create D, I need, obviously, D. I don't need E, and I don't need F. Agree? So far so good, it's trivial. Now, what is the expression for C? Expression for C is minus 2 times D. Agree? So therefore, for C, I will have to put minus 2 in here. Next one, minus 2 times E. I will have to put minus 2 here. Plus F. Right? I will need to put 1 here. Right? Are you with me? All right, good. So tell me what B is. So for B, I will need to 0 here.
I guess one base.
Minus 1 here. 0 here. And for A, so D will be multiplied by 1. E is not there. And F needs to be multiplied by minus 1. Okay? So we solved the system of equations. So part of it is trivial. You see that just 1, 1, 1. But this one, the top one, is not that trivial. But anyway, that's what we did. So a few observations. Observation number 1. That was a matrix 3 by 6. We had 6 unknowns, but the largest number of equations was 3. So therefore, we were only able to solve for 3 unknowns, and the remaining 3 had to be declared as parameters. Each parameter happens to be multiplied by its own vector, because these are just vectors with coefficients. Okay? So, bottom line, number of unknowns minus the number of equations is equal to the number of parameters. 6 minus 3 is 3. And that's how it works. So that's the formality of that. Now let's look at these vectors and just consider them from the point of view of linear dependence or independence. Well, you can see that zeros are in different positions. Okay? So therefore, we can reasonably assume that they are linearly independent. Remember that linear dependence means that you can take these vectors, geometrical vectors, and create a closed loop out of them. If you don't remember this fact, that's okay. That's not really relevant here, so we can live without it. But these vectors, there are signs of the fact that they are linearly independent, and this is indeed the case. So therefore, if you take these vectors and put them head to tail, you will not be able to stretch them and compress them so that eventually you will come back to the same point. So they are linearly independent. All right. Now, what goes next is quite important. So I will declare these vectors essentially as representative of my non-dimensional groups. Remember, the goal of this exercise was to find as many as possible independent groups. Because these vectors are linearly independent, so these parameters which we will obtain out of them are also linearly independent. So therefore are independent parameters. So I will go a little bit, I will explain this in more detail a little bit down the track. So what do I mean about those? Remember that these ones, these numbers, they represent powers, right? Namely, so if I go back, we see that that's where they appear. These are physical quantities raised to the powers. Okay? So, let me just read through this. So, the first value in this vector corresponds to A. A is the power of what? What quantity? Look at your notes. So it is L, right? Or did I have L? I think I had the, L is dimension, so I had this L, small l. Right? All right. L is raised to which power? 1. Okay, so it is L on its own. B is 0. C is minus 2. C is raised, is at the power of what? So, L divided by V squared, right? Agree? V squared. And then next one is D. And D is the power of what? Gravity, right? So it is LG divided by V squared. Well, you can check the dimensions of that. L is L, G is L divided by second squared, So it is L squared divided by secant squared and divided by velocity. Velocity dimensions of the velocity is L squared divided by t squared. So they cancel out. So you can see that this is non-dimensional. This is non-dimensional group. So, okay, let's see what happens with the second vector. Same idea. So the first is L, which is not there. So the second coefficient is -1. -1 is power of what? Rho, right? So it is rho. Okay. Next one is -2. So it is, which one? V. So it is V squared goes to the denominator. Okay. Next one. So A, B, C, D, E. Pressure. Right? Okay, good. So, and you can check that this is also non-dimensional quantity. You can just check that. So that it is pretty much becomes automatic. Pi 3 is equal to, and once again, going through this exercise once again. The first one is L, right? So it is L in the denominator. The third one is, the second one is V. And the last one, time. Okay? So T over L, or L over T is V, right? Sorry? Oh, sorry. V is, oh, where am I? Yep. Okay. Like that, right? Because it's first power, so therefore it is in the numerator, right? Okay, good. So, here we go. So basically this, what we obtained here is the statement of how many non-dimensional groups we can have. We cannot have more than 3. Only 3. At most 3. Remember what we started with? We started with a system of equations which contained 6 different parameters, physical parameters. And then the question was, if we have 6 parameters and we change a couple of them, or just one of them, does it mean that we will have to work out the new solution from scratch? And what we achieved here is the statement that not really. If these parameters somehow change, but change in such a way that these groups remain, these ratios become invariant, or remain invariant, then we don't really need to redo the whole job. We can work out the one solution which will fit into many, many cases with different groups, as long as these groups remain constant. Okay? For example, if I change V, say if V becomes twice as large, but so does L becomes twice as large. So then this ratio here will still remain the same. And therefore the solution which I obtained for the first computations will be still valid, non-dimensional solution, scaled solution. And all I need to do is to take this non-dimensional solution and extract individual quantities out of there and multiply them by their respective scales. So any sort of x variables will be multiplied by this L, whatever it is. If it is twice as large, so multiply by a quantity which is twice as large. Right? That's it. So physical solution is obtained by simply multiplying non-dimensional solution by a constant. Nothing else changes. So this is not like you need to solve partial differential equation from scratch. Is that clear? So that's what is important. But the benefits do not stop here. So first of all, right now we know that out of 6 possible variations in a physical problem, dimensional problem, in reality we only need to cater for 3 possible variations of these groups. If somehow these groups values remain the same, we don't need to do a thing. Solve it once and that's it. So that's important thing. But let me just ask you a couple of more questions about this. So how did I get these groups formally? So for example, pi 1. So what I did without telling you, I just said, well, let's look at this. But what does it mean if I look at this? That really means that I ignore these 2 vectors completely, meaning that I set E and F both to 0. If E is equal to 0, then this is gone. F is equal to 0, then this is gone. Not only that, I set D equals to 1. And then I will get this. Agree? That's what actually happens. So pi 1 is obtained by setting E0 to 0, F to 0, and D to 1. That's what actually happened. What if I do not set D to 0, or to 1, but I say D is equal to 2? What will happen with this group? So each of these will be multiplied by 2. Instead of L to the power 1, it will be L to the power 2. L squared. Instead of G, I will have G squared. Instead of V squared, I will get V to the power 4. So what that means that this parameter will remain its own, the same parameter, except it will be squared. So this is essentially a square or power of a parameter. So if this is a non-dimensional group, you choose D to equal to something like 2, 3, 4, and all you do is you changing the power of the parameter. Instead of the pi 1 being used directly, you will use pi 1 squared. So this is not considered to be of any significance at all. Okay? So that is something to keep in mind. So taking D, E, and F and declaring them to be anything but 1 means that you simply take the same non-dimensional group and rise it to the power. The nature of this non-dimensional group does not change at all. Okay? So therefore, these are chosen for convenience, not for any essential reasons. So for example, if you solve these equations and you will get somewhere, you will have 1/2, so which means square root of something. It's inconvenient to deal with the square root, so therefore you will, in that case, you will modify the prefactor so that 1/2 will, so prefactor, if the solution is 1/2, and prefactor is 2, 2 times 1/2 is 1, and you do not have these weird square roots. That's all it is. So that's one observation. Now, what if I say keep F as 0, but both D and E are equal to 1? What will happen then? So in that case, I will have this is power D. This is, well, doesn't show, well, let's look at what happened with the C. So if, for example, D is equal to 1 and E is equal to 1 as well, right? What will happen? It will be, C will be -2, -2, -4, right? So A will be 1 still plus 0, right? B will still be 0 minus 1. So D will be, so C will be -4. Next one will be 1. Next one will be 1, and the last one will still be 0. What do you think it will look like? So if so I'll just put the notes here. So here we will have 1, 0, 0. So D is equal to 1, right? Here we will have 0, 1, 0. Here we have 0, 0, 1. Okay, so these are triplets corresponding to D, E, and F. So what my suggestion is that now I choose the combination of these two, which means that I will keep D as 1, I will keep E as 1, but I still keep F as 0. How will it look? So in this case, what will I get? So let's just go through this exercise again. So it will be 1 plus 0. So it will be L to the power 1. Agree? All right. So B will be 0 minus 1. It will be divided by what? So the divided by rho. Okay. Next one, minus 4. So minus 4, it is the power of which quantity? Velocity. So it will be v to the power of 4 in the denominator. And next one, d is g. G will be raised to the power 1 plus 0, 1. So it will be numerator. Okay. Next one, a, b, c, d, e. E is equal to 1. E is what? Pressure. Multiplied by pressure, right? And finally, F still 0, right? So look at this expression. What can you observe? It's nothing else just by the product of the two. So therefore, again, individual groups did not change. You just multiply them. So therefore, this is not independent either. So products and powers are not considered to be independent. The groups are fundamentally the same. Okay? Good. So therefore, we concluded that we can only have 3 independent groups here, parametric groups. Therefore, the parametric dependence is on 3 groups, not on initial physical 6. That is important. So we reduced the dimensionality of our problem quite significantly by 50% just by doing that. But the next thing is to play with these parameters based on what we know about the physics or physical setup itself, without any going into any solutions, just trying to get some sense of these scales. So let's just go through them one by one. If we consider, for example, a flow bounded by solid plates, so fluid is contained between plates, 2 solid plates. So in this case, L could be chosen as physical dimension of this channel, so distance between the plates. So one plate here, another plate here, so the distance between them is, the width of the gap is L. That is sort of observable, experimentally observable quantity, right? So you can look at it, you can see it, you can measure it. Agree? So, all right, so in that case, we cannot do anything about that. So, all right, we keep it. What about G? G is gravity. Well, if we're here in the lab, so nothing we can do about it, right? It is G and that is G. So we cannot change it unless we take the whole system and fly it to a different planet, which is a little bit unrealistic. All right, so we cannot change G. What about V? Do we know anything about V? So do we have any idea how quickly the fluid goes through between this gap? So just by looking at this. So we can see the channel, we can see the plates, we can measure the distance between the plates. So we obviously can say that we know what G is, but velocity at this stage, we don't know, right? So at this stage, we don't really know, right? let's go a little bit further. P. Do we know anything about P? We said that P is there, right? So as a scale, but do we really know what it is? No. All right, we discussed V. What about density? Well, if we consider flow, say, of water, we definitely know what it is. So we cannot change it. So all right, so you can see what I'm getting at. I'm getting at the fact that in these parameters, some quantities, they are predefined and they're cast in stone. Well, pretty much carved in stone, right? So you cannot change them. They're given by physics, by nature. Nothing you can do about them. Others, not so sure. All right. What about T? Time.
No, you just say, well, this is one way, this is another way, and here closes the bit them. Or for buffer, you don't?
Just flows and flows. Whenever it stops, it stops. We don't know. At this stage, we don't have any information about that. Okay? So again, T is sort of up to discussion. Okay? So to summarize this, L cannot change. We can see it, we can measure it, given. G is given. Rho is given. V, P, and T, we don't know. If we don't know, then on one hand it is bad because we would like to know. On the other hand, it is good because we can play ignorance. And, well, what they say, if you don't know the law, it doesn't mean that you can offend the law, right? But in this case, we can. We can claim that we don't know what these three parameters are, so therefore we can choose them the way we like them. Now, the question is, what do we actually like, right? And the idea here is to simplify our life, right? So we all humans would like to have an easy life, and in particular, easy life when we solve the problem. So the fewer of these so-called degrees of freedom we need to deal with, the earlier we go home from work. Okay? We save our time by, if we, we had initially we started with 6. We reduced 6 parameters to 3, which is already great. But we have some ambiguities here, so why don't we just use those ambiguities to our advantage? How? Well, I don't know what T is, I don't know what V is. So what about if I just declare, I choose, I don't know what V is, I don't know what T is, I will choose that T is equal to L divided by V. I choose because I don't know what T is, I don't know what V is, so if I know what L is, but if I divide L by V, which I don't know, I still get something which I don't know. See the point? What happens here? If I choose this, what will happen to this parameter? That means that right? All right. So we fixed the degree of freedom. So now out of 6 parameters, initial parameters, we got 3, but out of those 3, we fixed one of them because we don't really care. We fix it strictly to 1. It is not a variable parameter anymore. We cannot change it. We do not want to change it anymore. It's just 1. Is that clear? Look carefully at what is left. Can we still play a game a little bit further? So remember, we cannot change L, G, or rho. They are given. But we don't know anything about V, P, and T. And we just played that game with t, but we still have p. Right? And what can I do with p? How can I create, declare what p is for my convenience? So if I choose p equals to rho v squared, then what happens? So that's what happens. So out of 6 to 3, from 3 to 2, from 2 to 1. Not bad. Not bad. All right, so we really have left with a single parameter. And guess what? V is still not chosen. So what do I do next? V is equal to LG square root. And P1 happens to be, in this case, 1 as well. Well, isn't that amazing? From 6 parameters, which potentially could drastically change the solution by very simple, by mathematical standards procedure, we reduced the problem to no parameters. Which means that if you solve the non-dimensionalized problem once, you solved it forever. Just forever. So, which means every single problem described by this system of equations is going to be solved in one go. Just think about it, how much help it offers, just this procedure. Okay? So therefore, what we need to do now is to take the original system of equations, introduce these scales into non-dimensional system, into dimensional system, and after that, we will see that everything will cancel out, and our system will have no parameters left at all, only differential equations. So differential equations with unit coefficients. No coefficients will be there. And we solve that system of equations. And once we've done that, we solved all the problems in the world, which fit into this, which can be described by Euler's equations. Can you believe that? All right. Now, technical step which I will ask you to do. So what I will ask you to do is now to introduce these scales into the original equation. So we determined the parameters, we determined the scales, so how t, p, and v are defined in terms of the rest of them. Okay? So what I would like you to do now is to introduce those scalings into the system of equations. And I remind you what the system of equations is. So that is the system of equations. If you are not comfortable with vector notations, then deal with this equation in continuity equation, and this equation written for in the component form. Okay? So what I ask you to do is the following. So how is it done? So once we determine the scales, so these are the scales that you will need to refer to, and I'll just create an extra page. So what I have here is the equation. D du by dt plus u du by dx plus, leave sufficient space in between, v du by dy plus w du by dz is equal to minus dp by dx plus, so, and I need density everywhere, so I'll need rho plus rho multiplied by g sub x. Okay, so this is just the component of the gravity vector in the x direction. So x could be not necessarily horizontal, it could be under some angle with respect to gravity. All right, so this is our equation of motion in the x direction. So we know that u is equal to, so it is scaled with v, right? We know what v is, it is square root of something, but I just keep it as v, right? So I will do that substitution now. So this is the scale, and this is essentially the ratio between the physical function u that we are trying to do, and u star is simply that physical function divided by the scale v. Okay? So similarly, I will have t, which will be t multiplied by t star. We will have p, which will be capital P scale multiplied by p star. So what else is there? And we also have x, y, and z, which are L multiplied by x star, y star, and z star. So you can see what these start quantities represent. So they essentially are the original physical quantities divided by their respective scales. All right? So what I will ask you to do is to replace every single term in these dimensional equations with their scaled version. So essentially this will be, like I'll show you what I mean. So rho, this one is du, and this will be u star, du star by dt star. And of course, because these are constants, we can pull them out of derivative. So this will be v divided by t. So that's how the first term unfolds. Okay, is that clear? So I will ask you to do the rest of it. Okay, so do the rest of it. So substitute this. Well, if you have your space left, so basically fill these gaps with the scales and put the stars in the right positions. Okay, so I'll let you work on this for a few minutes. once you've done all this, then they become definitions of various scales from the previous page. So for example, T is V divided by L, right? Oh, sorry, T is L divided by V, so this coefficient here will become therefore V squared divided by L. Okay. So the bottom line is that if you do everything correctly, and once you look at what the constant scales appearing in the left-hand side are, and what you have on the right-hand side, you will see that they are the same, and you can cancel them out. You can divide through by them, and if you do, then you will get du star by dt star plus u star du star by dx star plus v star du star by dy star All right, so I'll let everyone finish this, but that is what you should get. If you do not get that, so let me know, then probably there is some sort of error in your computations, in your writing.
Why? Last
Yes?
yes.
So, okay, so, all right, I was a little bit quick here, so, okay, good thing that you noticed that. Let me just correct myself, or rather, be more pedantic here. So, G sub x, that's this term. So we have rho on the left-hand side, we have rho on the right-hand side, it will cancel out. But then we will need to divide by this coefficient, v squared multiplied by t. And v squared and L, well, not L. Agree? Is that right? So let me multiply this by G and divide by G. Agree? Is that clear? So obviously if I multiply and divide, then nothing changes. But now, what can you say about this? Look at the previous page. That's 1, so therefore it will be G and projection of G on onto the x direction. Is that clear? So it's late in the day, so if something is not quite clear, so we have about 5 minutes left. So I'm happy to take it slowly and just make sure that everyone is on the same page. Just be honest. If you have any algebraic difficulties, let me know. We have time to move on, to discuss everything, and then we will, once we catch up with everyone, so we will move on. All good? All right, I will assume that everything is good, so you understand what is happening. One more thing before we stop for a break, and then after that we will do something else practical, like tutorial. G sub x and g. So g is a constant, pretty much constant. That is gravity on the Earth surface, right? So it is constant, physical constant. Constant. G sub x is essentially projection onto the, so gravity is, we will usually draw it as a vertically pointing down. If x is in this direction, G sub x is essentially projection. So G sub x is just this component of the. Is it clear geometrically what I mean? So this is x direction. The gravity is pointing straight down. X is under some angle, so we have some sort of inclined channel, for example. So therefore, we simply project G onto the x direction. And if we do that, we will just, from this rectangular triangle, so this is a triangle, rectangular triangle, this is just G multiplied by the cosine or sine of inclination angle. It's very trivial, okay? I don't want to actually go into these details. The important thing which I would like to emphasize, that even though this is a projection, it is a constant, because it comes out of a constant vector. Gravity is constant, so whatever you do with the constant, it will remain constant. Agree? So therefore, the bottom line is that whatever you have here is constant. Agree? Now, if it is a constant, if I multiply it by x, and then I will differentiate it with respect to x, what will happen? You will get it back, right? So this will be the original constant. Agree? But guess what I can do? I can write dp by dx minus g sub x divided by g multiplied by x. See that? So I can push this term, constant term, into the derivative. And then I will do something insane. Oh, sorry. So I will tell you what I will do after the break then.